Hi everyone, in this video we're going to go over section 6.1 on set theory. So this is going to be a little bit of a review of some of the ideas of sets that we previously saw on the first chapters. So what are sets? Sets are collections of elements or objects, and those elements are the individual item that belongs to a particular set. We have the notation A belongs to A, which means A is an element of the set A, and A does not belong to the set A, or A is not an element of the set A. Here, the key properties of set is that order doesn't matter. If we have the set of 1 to 3, that's going to be the set of 3 to 1 is the same thing. And repetition doesn't matter. That's the biggest difference with sequence. So for example, we have 1, 1, 2. This is just equivalent to the set of 1, 2. Now, we have some important set of numbers that we've been using. We have the natural numbers that start from 1, so 1, 2, 3, 4, and so on. The integers that include all the naturals, 0, and all the naturals negatives. The rationals, which are the fractions of the form p over q, with p and q integers and q different from 0. The real numbers, which are all the real numbers on the real line, all the numbers on the line. And we have this relationship in terms of subsets. The naturals are a subset of the integers are a subset of the rationals, and the rationals are a subset of the reals. Now let's go back to set notation. So we have a couple set notations that are possible. We have set rooster notation, which is specified as set by writing all the elements between braces. So we have the 1, 2, 3 here, which is a set containing exactly 1, 2, and 3. We have the 2, 4, 6, 8, dot, 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 which here will mean by all positive even integers. The dot, dot, dot implies the continuity of the pattern that we have over here. Now we can also have collections of other things. We have the ABC set here containing only letters. And once again, regardless if it's numbers or letters, order is not going to matter, and repetitions will be ignored when talking about this a set being the same. The set builder notation, on the other hand, describes a set by specifically doing a property that that its element must satisfy. So for example, the general form is x that belongs to S so that p of x. So for example, the set of all the x in S such that the property p of x is true. One example of this will be the n that belongs to the integers so that n equals to k. For some k that belongs to C+, this will mean all positive even integers. An interval notation, so for example, the x that belongs to R, so that x is between -1 and 3. And so these are all the real numbers, inclusive from -1 to exclusive 3. We can also have something like the n that belongs to the integers, where n squared is less than 10, and this will be the integers whose square is less than 10. You can find this also in rooster notation. This will be just 0, 1, 2, and 3. Now let's talk about subsets. So once again, a set A is a subset of a set B, or A is a subset of B if and only if every element of A is also an element of B. Symbolically, this means that A is a subset of B if for all x that belongs to A, then that x is going to belongs to B. Some examples of this, for example, the set of 1, 2 is a subset of the set 1, 2, 3. The set of AB is going to be a subset of AB. Every subset is a subset of itself. Now, the set 1, 4 being a subset of the 1, 2, 3, something false, because 4 is not on the 1, 2, 3 set. So that's one example when it's not going to be a part of the subset. It's not going to be a subset. Now, in terms of negation, A is not a subset of B means that there is at least one element in A that is not in B. Like in this example, 4 is here, but it's not here. So that's why it's not a subset. Now, let's talk about proper subsets. A set A is a proper subset of B, or written A subset of B without being equal if A is a subset of B and it's not equals to B. Symbolically, that means that A is a subset of B, is equivalent to A being a subset or equals to B, but it is an X that belongs to B such that it's not in A. Okay? Examples of this will be the set of 1, 2 is a proper subset of 1, 2, 3. Notice that 3 is here, but it's not here. And AB is not a proper subset of AB because they're the same. The naturals are a proper subset of the integers because you have more integers than just the positive naturals. The key difference here is that A contained equals to B allows for the possibility that A is equals to B. Well, A subset of B requires that A is different from B. So you're going to have an element that is not part of that. Now, two sets are equal if and only if every element of A is in B and every element of B is in A. Symbolically, A is equals B if A is a subset of B and B is a subset of A. Now, to prove that A is equals B, you need to prove both of these directions. So you need to prove A is a subset of B, so every element of A is in B, and you must prove that every element of B is in A. Example here will be 1 to 3 and the set of 3 to 1, because the order doesn't matter, they have the same elements. Now let's talk about special sets. So we have the empty set, which is the set with no elements. The empty set is going to be a subset of any other set. Why? Well, let's assume that empty is not a subset for any other, for some set. Then it's going to exist an element X that belongs to the empty set, so that it's not an element of A. But empty has no elements, so we have a contradiction. Therefore, empty gotta be a subset of every single set. Now, the universal set, or universe of discourse, denoted by U, is the set of all the elements under consideration for a particular discussion. So, for example, when discussing properties of the integers, we can talk about the universe being the integers. When discussing geometric points in the plane, we can say the universe is R2. When discussing the student in this class, well, we're talking about all the students on Math 1071. The universe is a set that provides context for all the other sets in a discussion. Now let's set operations. So set operations, we have a couple of those. We have the union, and for two sets A and B, the union is the reunion of all the elements in A together with B, or all the elements in A or in B. Symbolically, this means A union B are the X, so that X is of A, or X is from B. Some examples here. If we have the set 1, 2, 3, union with the 3, 4, 5, then the union is going to be the set 1, 2, 3, 4, 5. Remember, there's no repetition, so it doesn't matter that we have 3 twice. The set of A, B, C, D, union with C, D is going to give me the set A, B, C, D. And the union of the set 1, 2 with the 3, 4 is just going to give me 1, 2, 3, 4 in a set. Union combines all the elements with both sets. We don't have duplicates. Now, intersection of two sets is the common elements in both A and B. Symbolically, we denote this with the symbol A intersection B, and as the elements that are in A and are and B at the same time. So at the same time, X belongs to A and X belongs to B. For example, if we take the intersection of 1, 2, 3 and 2, 3, 4, notice that 2 and 3 are common, so that's going to give me the intersection. If I take A, B, C intersected B, C, D, once again, B and C are common, so that's the intersection. If I do the intersection between 1, 2, and 3, 4, notice that there is no common element, so these sets are disjoint, and the intersection is empty. Okay? The intersection is going to contain only elements that shows up on both of the sets. Now, the difference on sets, denoted by A difference B or A minus B, is the set of all the elements that are in A, but they're not in B. So we're pretty much taking A and subtracting the intersection, removing the intersection of common elements. So A minus B is X that are in A, but not in B. So for example, if we take 1, 2, 3, 4 minus 3, 4, 5, then we're essentially removing 3 and 4 because those are the elements that are in A that they're not in B. So we get 1 and 2. If we have A, B, C, and we're subtracting B, D, so the element that is common is B, so I remove the common element. If I have 1, 2 minus 3, 4, because they don't have any common elements, the subtraction is just going to be the same number, the same set, the set of 1, 2. In general, A minus B remove from A any elements that are in B common. Notice that A minus B is very different from B minus A. Now, if U is the universal set and A is a subset of U, the complement of A, denoted by A to the C or A bar or A tilde, is the set of all the elements that are in U but not in A. Okay? Symbolically, we can see this as the universe minus A, or the elements that are in the universe that are not part of A. Let's see an example here. We have U, the universe here is going to be all the numbers from 1 to 10. And A is going to be the pairs, 2, 4, 6, 8, 10. So the complement is going to be, or the evens, 1, 3, 5, 7, 9. The complement depends of the universal set. Now, more special sets are going to be the power set and the Cartesian product. The power set of A, denoted by P of A, is the set of all the subset of A. Okay? So this is essentially a collection of all the possible subsets. Now, if A has n elements, then parts of A, or the power set of A, is going to have 2 to the n elements. One example. Consider C the set of 1, 2. Let's find part of C. First and anything, notice the empty set is always a subset, so it's going to be there. The set of 1, the set of 2 is going to be there, since each of the elements, you can consider one small subset with each of the elements, and of course itself. So all this are subsets of C, and this collection of 4 elements is going to give me parts of C. Notice that this is all the subsets that are, because this has 2 elements, so parts of A needs to have 2 to the 2, so 4 elements. Now, the Cartesian product of sets A and B, denoted by A times B, is the set of all the ordered pairs A comma B, where A belongs to A and B belongs to B. Symbolically, A times B is just the set of pairs AB with A and A, B and B. So let's do an example. A is the set of 1, 2, B is the set of X, Y. So A times B is going to be 1x, 1y, 2x, 2y. This covers all the possible pairs that we have between A and B. Okay, so important facts here. The pair AB is different from the pair BA unless A is equals B. And if the cardinality of A is M and the cardinality of B is N, then A times B is M, has cardinality M times N. So that's the number of elements. In general, A times B is different from B times A. Now, last, to conclude with the introduction to things in sets, in the reminder of things in set, we have the interval notation. So for subsets of real numbers, let A be in R with A less than B. So we have the following. We have the open interval, which is all the elements in R that are less than B, bigger than A, not inclusive. We have the closed interval, which is all the elements that are in between A and B, less than B, bigger than A, but including A and B. We also have the half open interval, which is going to be open in one of the extremes, all the elements between A and B, but either not inclusive in B or not inclusive in A. And we have infinite intervals that go from a single element, for example, from A to infinity, including or not including A. And this is just going to be simply B, the X bigger than A in the not inclusive case, or X bigger or equal than A on the inclusive case. For B in the other direction is also something similar. If we have minus infinity to V, not inclusive on both sides, this is just really the set of X that belongs to R where X is less than B. This is including all the elements here. And of course, the real numbers are given by minus infinity to infinity. Okay, remember here that the parenthesis means that the endpoint is not included. The bracket means that the endpoint is included. And always use parentheses with infinity and minus infinity because they're not real numbers. And we're never really touching infinity. Now, some example of this will be the closed interval from minus 3 to 5. That includes both minus 3 and 5. Minus 2 to 4 open, which is not going to include minus 2 or 4 either. 0 to infinity, that includes 0, but not infinity here. And minus infinity to 7 close, which includes 7, but not minus infinity. Okay, summary. So here in this section, we did a bit review on sets. We check those are collections where order and repetition doesn't matter. We check, again, the notation and Rooster or set builder and the subset definition, where every element of A must be in B for A to be a subset of B. The operations, union, intersection, different, and complement. And the power set that has 2 to the cardinality of A elements and includes all the possible subsets that A has. The Cartesian product that has A times B elements. Next, we're going to go with the important part of this section, which is set identities and actually doing proofs with sets. So in this particular section, we were mostly reviewing a lot of different things in set that you should know, that you should be aware. And now we're just going to jump and proving things with sets.